All right, next practice problem for you guys. This is one where I'm going to do a practice problem. It might not be exactly like ones that you see in the homework. It just depends. Because this is, they called it in the book integrating concepts or whatever. Like it's basically saying they're using ideas from other units and other information that we should know to sort of all put together and have an idea and um, solve the problem. Okay, so let's just walk through this one and see how it goes. Um, a sample of 70.5 milligrams. This is from page 153, by the way. A sample of 70.5 milligrams of potassium phosphate is added to 15 milliliters of 0.050 molar silver nitrate, resulting in the formation of a precipitate. Part A, write the molecular equation for the reaction. Okay, so molecular equation. So we've got some information. We've got potassium phosphate. So potassium, K is a +1. Phosphate, PO4, 3 negative. Cross down, we end up with K3, PO4, right? All right, and it doesn't say if that's a solution. I'm assuming it is just because it says results in the formation of a precipitate. We can always check. PO4 is actually solid unless alkali metal cation. Potassium is an alkali metal, so this will be aqueous. All right. Plus silver nitrate. So silver is Ag is a +1. Nitrate, NO3 is a -1. Cross down, you end up with Ag, NO3. And I know that all nitrates are aqueous, no matter what. So AQ. All right, yields. Okay, now this is a double replacement type deal, right? So we're going to take the K with the NO3. So we're going to end up with KNO3. That's +1 and -1. So it's just KNO3. And again, like I said, you could check your solubility table. I know from that table that all nitrates are aqueous, so this will be aqueous. Okay, plus that means we're combining the silver with a phosphate. So silver is a +1, phosphate's a -3. So we should have Ag3PO4. Okay, now they said in the formation of a precipitate, that means this should be a solid. I'm going to double check on my solubility rules table. PO4 is a solid unless it's an alkali metal or NH4. Silver is not an alkali metal or NH4, so this will be a precipitation reaction and solid. Okay, now balancing, let's see. So we would need a 3 in front of this and a 3 in front of this for balancing. Okay, there we go. Balanced molecular equation for part A. All right, part B. What is the limiting reactant in the reaction? Okay, so limiting reactant. This goes all the way back to like our BCA charts and that kind of stuff. So to do a limiting reactant, if you recall, what we really need is we need the balance equation, which we have, and we need the moles of each reactant. We need to know how many moles of each we start with. So what we're looking for, because what we want to do is we want to take the moles of K3PO4 and we want to divide it by the coefficient, which here is just 1. Okay, and then we're going to take the moles of AgNO3. Sorry, it took me a second to catch my brain back up. And divide it by its coefficient. Okay, and then what we're going to do is, remember, we compare those two numbers. Whichever number is smaller, that substance is the limiting reactant. All right, so what we need is we need moles of each of these. So let's look and see what they gave us and see how we can get that. All right, so moles of K3PO4. Okay, so I'm going to actually do these. I probably should have done it up here in a different color, but so moles of potassium phosphate. All we have is milligrams, right? And we've got milligrams of that, and we've got let's see, we've got a molarity, and we've got milliliters of silver nitrate. So the second one, actually, the moles of AgNO3, we can actually get that by, so I'm just going to kind of circle this in blue. So, oh, you know what? I almost forgot. I am using, look at that, using erasable ink. So, okay, so I can do the moles of, what was it, silver nitrate, AgNO3. And that's going to be over the coefficient. And I can do this one as well. I'll do this in red. Okay, moles of K3PO4 over the coefficient. Okay, so now that I've got those color-coded, all right, so I'm going to get the moles of AgNO3 by using this. The same way that I did it on the last example, and I'm going to start with the 15. With the 15.0 milliliters. And I'm going to convert from milliliters to liters. Okay. Then I'm going to use the molarity as a conversion. So I'm going to go from liter to moles, 0.050 moles, and we're talking of the AgNO3. Okay, and that's what we want. We want it in moles, right? So equals, see what this comes out to be. Significant figures, we've got 3, and that's technically 2, so it'd be 2, so 0.00075 moles of AgNO3. All right, so that is going to go up here. Divided by 3, which is going to give us 0.00025. All right. Now, okay, so how are we going to get moles of K3PO4? Well, similar to what we did before, we've got a balanced equation, right? Now we know the moles of one thing, we can actually convert to see how many moles of the other thing we would need to hold on a second. I need to look at something. Okay. Yeah, sorry guys. I just realized something. So this, I looked at it too quickly. This is 70.5 milligrams of potassium phosphate. So milligrams, not milliliters, milligrams. So that means that's a solid. So it's not a huge deal, really. Although if it's a precipitate, wow, I don't like that idea at all. Well, it doesn't really matter 100%. I'm going to leave it as aqueous. It doesn't really matter 100 really for this, what we're doing here, other than the fact that when we're finding the moles of K3PO4, you need to make sure you recognize that that's milligrams. That's a mass. Okay, so to find the moles of this, all we're going to do is take, I was making sure I had enough room here, but I don't need all of that. So I'm going to take the 70.5 milligrams of the, let's see, K3PO4. All right, and we are going to change milligrams to grams. Then we are going to go from grams to moles. Okay, K3PO4. So that's, let's see. Phosphorus is 31. Oxygen is 16. So we get, it's 212.3 because potassium is 39.1. 212.3 grams for 1 mole. Remember, we're talking about the K3PO4. Okay, so we end up with 0.000. Significant figures for this would technically be 3. So 332 moles of the K3PO4. Okay, so that we're going to put up here. And I'm running out of room. Oh, but that's just the same, right? So that's just going to be because it's just divided by 1. So actually, well, that's fine. Okay, so we're comparing this and this. Which one is smaller? Okay, this one is smaller. So that means your limiting reactant is this one, AgNO3. All right. Now, part C, because yes, this is not done yet. All right. Calculate the theoretical yield in grams of the precipitate that forms. All right. So theoretical yield. There's a couple of ways you can do this. Okay. What I'm going to do is I'm going to walk you through the sort of like the BCA chart in terms of like where stuff would go. And then I'm going to show you the dimensional analysis way, okay? So the BCA chart, okay, I'm not going to rewrite the equation. Just first, second, and then third and fourth, okay? So we've got our first thing is the K3PO4, AgNO3, KNO3, and Ag3PO4, right? And so I'm going to leave space for 1, 2, like 1, 2, and then the halfway, the KNO3. So all we're really looking for, right? The grams of the theoretical yield of the precipitate. So the precipitate that forms, right, is, I'll try to use a slightly different color maybe, use a lighter shade of blue. Is, actually, let's see if, hold on, test out here. You really can't see that, can you? That's nice. It's erasable. Give me erasers. All right, let's try this. Let's try this blue and see. Okay, so the precipitate, if we look up here, is in grams. So what we want is grams of Ag3PO4, right? Because that's our solid. So that would be the precipitate. Okay. So remember, the whole BCA chart is all in moles, right? So what we're going to do is we want the moles of this, and we're going to turn it into grams. So where would that be? Well, that's the thing here. So where would the number of moles, the theoretical yield, or the amount that forms theoretically, would be here? Would be in this spot, right? Okay, now we know that in our BCA chart, the products are always 0 moles to start off with, right? Okay, so over here, you don't really need this, but just to kind of give you the idea, you would have K3PO4 was first, so it'd be like 0.000332, and then the AgNO3 is 0.00075 was the moles of AgNO3 that we started with, right? Okay, now here's the key. How do we get the change row? Because all we really need is this column. So the change row, remember, is the number that we use to find the limiting reactant. So after we divided by the coefficients, the smaller number, the one that tells us the limiting reactant, times the coefficients in the reaction. So 0.00025 times 1. Okay, all we really need is this column. You could fill in these if you wanted. Do the 0.0025 times the 3 times the 3 times 1 there. We don't need them. So remember, for products, you just add down. So we end up with 0.00025. Okay. Now remember, this is in moles, right? So we're going to do moles Ag3PO4, and we're just doing a conversion. Ag3PO4 into grams. So let's see. Silver Ag is 107.9. So times 3 plus phosphorus is 31. Excuse me. So it's 418.7 grams for 1 mole of Ag3PO4. And we just do the math. We get significant figures would be 2. So we get 0.10 grams Ag3PO4 is your answer. Okay. Now, let me show you a second way. I'll do this in, maybe I'll just, no, because I already got some black on there. Let me do it in, what other colors do I have left? I got this pink color here. Okay, so this would be like method 2. All right, and in this way, what we're going to do is we know that. Okay, sorry. So we know that AgNO3 is our limiting reactant, correct? That means the amount of limiting reactant we have determines everything else for our equation. So if we start with the AgNO3, the moles of AgNO3. Now, remember, we want to start with the moles of AgNO3 that we have at the beginning, not the one that we use to find the limiting reactant after we divide by the coefficient. Okay, so we want to start with this. So we're going to start with 0.00075 moles of the AgNO3. And we're going to convert from moles of AgNO3 to moles of the precipitate that forms, which is the Ag3PO4. Okay, these numbers, remember, come from the coefficients. So in front of AgNO3, we have a 3. In front of Ag3PO4, there's nothing, so it's a 1. Okay, then we go, we want grams of the Ag, so we just go from moles of the Ag3PO4, and we go to grams. So this is the 418. This step is the same as that, so it's the 418.7 grams. And guess what? We're going to end up with the exact same answer. Okay. Doesn't matter which way you do it. The method one way, like this, or the method two way, doesn't really matter which way you do it. Whichever way makes more sense to you, do it that way. All right. So that one took a little longer, but kind of had some more parts with it. If you have questions, as usual, just let me know. Good luck, guys.